Okay, today we're going to be continuing our conversation, our talk on vector addition. But this time we're going to look a little bit more, instead of using geometry, we're going to be using trigonometry. In the previous talk, we talked about adding them head to tail and subtracting them head to tail. Now we're going to actually be using the idea of trigonometry to add vectors and break vectors into the components. For example, sometimes vectors are perpendicular to each other and can be added using trigonometry. So if we have a vector A and a vector B, it obviously is equal to vector R, the resultant. But what is this length without doing it graphically? We can use the tools of trigonometry. Oops, excuse me. So for example, let's say that this side here is 2, this side here is 6. We could use Pythagorean's theorem to find out the resultant. Our resultant would be 2 meters squared plus 6 meters squared. Take the square root of that to get the resultant, and you get 6.32 meters. But that's not enough to determine what this vector is, because each vector has to have not only a magnitude but a direction. Like, for example, this vector is 6 meters but in the positive x direction. This is 2 meters but in the positive y direction. This is 6.32 meters, but in what direction, we have no idea. So we need to find out this angle. And if you remember, we're going to use our old friend, the tangent. All right. So we know the tangent is 2 meters over 6 meters. So we know that. So we're going to ask the calculator, hey, for that ratio, tell me the angle it works for. And when we do that, it comes out to be 18.4 degrees. So the correct answer of the resultant of the 6 meters to the x, 2 meters in the y, positive y, would be 6.32 meters at an angle of 18.4 degrees above the horizontal. Excuse me. All right. All right, so what we've been alluding to is the idea that vectors can be broken into components. And a lot of times it's easier to add them in their components, because what we could do then is we can break this vector into how much if it's in the x, how much is in the y, and then we can easily add it to another vector after we break it into its components. And then what we do is just add up all the x's and all the y's, and we're pretty much done. All right. So, a vector component of A are two perpendicular vectors ax and ay that are parallel to the x and y axes and add together vectorially so that A is equal to ax plus ay. Now, obviously you cannot just, if this was 2 and this was 4, add it together and get 6. You have to add them as vectors using Pythagorean theorem and the arctangent. All right, so now let's say we were trying to add vector A to vector B. We can graphically see that doing the head to tail method, it comes out to be C. But let's say we don't want to actually use the head to tail method. What we need to do then is to take vector A, find its components, the x and the y. Vector B, find its components in the x and the y. Add all the x's together, all the y's together, and then we'd be able to find out. Okay, your book talks about the idea of unit vectors, which I think are a good idea, but it sometimes gets a little confusing. What a unit vector basically means is, like, if you look at this is the unit vector x. It's 1 unit long in the x direction. So to find out a total vector, you would take the magnitude of x times the unit vector x. The magnitude of ay times unit vector a of y, and so forth. And then you're able to just add them together. The only reason I'm pointing that out is I do not like using it because I think it just confuses the fact. When we're actually talking about this, when we break it into components, we know that the x component is in the x direction. We don't have to multiply it by unit vector. We realize that already. So I'm not going to make a big deal of it, but I just wanted to point it out to you if you were reading in your book. You got a little bit confused. Okay, so now I'd like to talk about how we can actually use this idea. Let me start you off with an example. This is an example using displacement and distance, which we'll cover in the next unit on one-dimensional kinematics, but it will give you, it's a good introduction to vectors, and I figure it would be good, at this point it would be a good point to show you how to do it. So here we go. A boy who was hit by a 5-gallon bucket of driveway sealer falling from the top shelf of Home Depot is wandering around the store. He first walks 5 meters north, then 12 meters east, then 2 meters north, and then 8 meters west before he collapses and dies. I know that's kind of sick, I'm sorry. What was his distance he covered, and what was his displacement? Okay, we'll start off by actually drawing the vector, or the diagram. So, we have the following situation. We went up 5 meters. Then we went over 12 meters. Then we went up again 2 meters. And then we went over 8 meters. And what we're trying to do is we're trying to find out the distance from here to here, excuse me, the displacement from here to here, as well as the distance you traveled. Now the distance you traveled is pretty simple. The distance would just be 5 meters plus 12 meters plus 2 meters plus 8 meters. And that comes out to be 10, 22, 27 meters. That would be embarrassing if I did that wrong. Okay. All right. Okay, so we know how to do the displacement, the distance. Now I'd like to talk a little bit about how we would do the displacement. What you need to do in problems like this is to break it into components. How much is in the north and south? How much is the east and the west? I'm going to call up and to the right as positive. So, if I count this as north and south, this is east and west, I can find out how much of each of these are in each direction. So I have 5 meters going north, but nothing east and west. Then I have nothing north and south with this one, but 12 east. Then I have 2 north, okay, but nothing east-west. And then I have nothing north-south, but 8 east-west. So I want to find out the total of that. So, by the way, this has to be negative. Why? Because it's in the opposite direction of what we called positive. The positive direction is pointing to the right, and we're pointing to the left. So if we add all these up together, we get 4 meters. Positive means to the right, and 7 meters, positive meaning up. So that means we have a vector now that is 7 meters up and 2 meters over. And what we're trying to do is find this resultant. Okay? All right. So to do that, we'd use Pythagorean's theorem. And that would end up being 2 meters. Well, let's use a different color. Why is it coming out so thick? Okay, that's better. 2 meters squared plus 7 meters squared. Take the square root of that, and we end up with 7.3 meters. But that's not good enough. We need more to define this vector. we need to know the angle, and I'm going to define this angle. Okay? And to define that angle, I would take the arctangent of 2 meters over 7 meters. And that comes out to be 15.9 meters. Excuse me, degrees. So this means that this resultant is 7.3 meters at 15.9 degrees east of north. In other words, I'm defining this angle here. I'm going 15.9 degrees east of going north. All right, so that problem was a little sick. Poor kid got killed. So let's try another one and bring him back to life here. After the boy died, his father was so upset he wandered around the store in confusion. He walked 5 meters north, then 12 meters east, then 8 meters at an angle of 25 degrees north of east, before he realized his son was not dead, but only faking it as part of a new reality show about scaring parents. Obviously, it only aired for 1 season because, well, it was so horrendous. Once again, we want to know what the distance covered is and what was his displacement. Okay? All right. So let's try this problem. All right. So we went 5 north. Then he went 12 east. Oops. And then he went 8 meters at an angle of 25 degrees. Okay, so this angle of 8 meters at 25 degrees, this cannot be added easily. We have to actually take it and break it into components. We have to figure out how much of it's going over. Okay, how much of this vector is going over, and how much of it is going up. Okay, if we do that, to do that, we actually have to use sine and cosine. So this would be, this side here would be 8 meters. Sine, because it's the opposite of the angle, 25 degrees. And when you do that, it comes out to be 3.38. Now that's not correct sig figs. I carried one too many, but I'm going to carry the extra until I'm done with the problem. And in the x component, I would have 8 meters. Sine, nope, excuse me. Cosine of 25 degrees. And that comes out to be 7.25 meters. What this now allows me to do is I'm able to take this vector here, this 8 meter vector, and it's really gone now. It's being replaced by these two. Okay? So now I can go back and I can add up all my components, north, south, east, west. Okay. Initially, the first vector, you were going 5 meters north and nothing east-west. Next one, you were doing 12 meters, excuse me, you were doing nothing north and south. But 12 east. And the next vector, you were doing 3.38 8 meters north and 7.25 meters east. When you add up all those together, get out of the way, you get 19.25 in this direction and 8.38 in the north-south direction, which means now we can rewrite our whole vector as being 8.38 meters up and 19.25 meters east. Notice I didn't do them exactly the correct length, but they should be somewhat representative, okay? You wouldn't want the 8-meter long vector to be longer than the 19-meter long vector. And to find the resultant, you would use Pythagorean's theorem. You would take your 19.25, square it, your 8.38 meters, square it, find the square root, and then you would also find out the resultant angle. Okay? Let's actually do that really quick. It's 19.25 meters squared plus 8.38 meters squared. Take the square root of that and you would get your answer. I don't have a calculator with me right now, so I can't really do it. And the arctangent of the opposite side of this would be 8.38 over the adjacent side of 19.25 meters. And that would give the resultant angle. And this is why we would want to take vectors and break them into the components so we can add them easier. And we'll do more problems with this as we go into the next unit as well.